This is just a short little video to tell you the relationship between constant finite differences and the leading coefficient of a polynomial a. And just a reminder, what I mean by that is if we have a function equal to ax to the n plus etc., more terms down there, how can the finite differences, when we finally find a constant finite difference, tell us something about that leading coefficient a? So I've got some finite difference tables here, or at least I'm going to soon have finite difference tables here for a linear, a quadratic, a cubic, and a couple of quartic functions. And I'm really quickly just going to do the finite differences on this. So when we do that, I think you'll really quickly see that those are all ones. On this one, I get 3, 5, 7, 9, 11. And when I do the second differences, I get 2, 2, 2, and 2. And again, I'll remind you that the exponent on there, and remember that for linear, the exponent is a hidden 1, tells you which difference will give you the constant. Oops. Let's go over there. Second difference. For the x cubed, we should get the third difference. So let's hope the third difference is constant. I think the numbers here are 7, 19, 37, 81, 61, 91. Second differences will then be 12, 18, 24, and 30. And the third differences, which is the one we said would be constant, looks like they're all 6s. Okay, so third differences are all 6s. How about fourth differences? Okay, that's going to be 15, 65, 175, 369, and 671. Those differences will be 50, 110, 194, and 302. Those differences will be 60, 84, and 108. And those differences will be 24 and 24. So there we get our constant at the fourth difference. Now, I'm not going to actually do this one in full, but what I want to show you is that if I did the first differences on this is just y equals 10x to the fourth as opposed to y equals x to the fourth we did. You'll notice all the y values are just 10 larger, and as it turns out, the first differences are going to be 10 larger. So that's going to be the 150, 650, 1750, 3,690, 6,710. And I'm not going to do them all because it's a pain, but the final results are going to be 240, 240. Okay, so here's what I want to point out. If we look at all things that have coefficients of 1, so the x squared, x cubed, x to the fourth, leaving out that last table, the constant first differences were 1, 2, 6, and 24. 1, 2, 6, and 24, where the largest term, n, was 1, 2, 3, and 4. Is there a pattern there? 1, 2, 6, and 4. There is. It's actually called n factorial. And n factorial by definition is just n times the number below it times the number below it times the number below it all the way down to 1. And so 1 factorial is 1 and you're done. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, which is 6. And 4 factorial is 4 times 3 times 2 times 1, which is 24. And you'll notice that for our graphs, that's the constant differences we were getting. Now, when we made our A10 in the last one over here, that just made our constant finite differences 10 times larger. So as it turns out, the constant finite difference And you know what? That's a lot to write. So why don't I just call it f, constant finite difference. The constant finite difference is going to be n factorial times a, or just a n factorial. And quickly rearranging that, you can see that the leading coefficient, so the number that goes in front of the largest degree in a polynomial, is just going to be f over n factorial. So those two equations, which depends which form you'd like, can help you solve problems. So if you know that a certain finite difference is equal to a value, you can divide it by n factorial to figure out what a will be. And likewise, if you want to know what the finite difference is going to be when you expand it out, the constant finite difference, you just take a times n factorial. And that is all.